Hello everybody. In this video we're going to be covering section 10.6 in our text entitled Lattice Structures in Crystalline Solids. This is actually a pretty big topic, so we're only going to be really providing an overview of it. That said, this is still going to be a little bit of a longer video. Our learning objectives: first we're going to describe the arrangement of atoms and ions in crystalline structures. We're going to be able to start to compute ionic radii using unit cell dimensions, and we're going to explain the use of X-ray diffraction measurements in determining crystalline structures. Let's start by discussing what we call the unit cell. So we've seen before that crystalline solids are closely packed atoms in a repeating pattern. The unit cell consists of lattice points that represent the location of atoms or ions, and they are the smallest repeating unit of the overall structure. So if I take my unit cell and I just repeat that over and over again, that's what's going to lead me to the overall crystalline structure. Elements and compounds that crystallize with the same unit cell structure are called isomorphous. So here we have an image of a unit cell. If you imagine that each of these are atoms, these are what we call our lattice points, and the volume that that takes on would be our unit cell. And again, we can imagine propagating that out in 3 dimensions to make up our crystalline structure. There's something called the coordination number, and what this is the number of other particles that each particle in a crystalline solid contacts. All right. So for instance, a atom right here can go to any one of these different 6 points, and it's in contact with all of those. So the coordination number for that atom would be 6. Let's start off by talking about the structures of metals. The simplest unit cell structure that we could have is actually called the simple cubic. They have atoms lying on the corners of a cube. This is an inefficient method of packing the atoms. Only about 52% of the overall volume of the unit cell is filled. This arrangement leads to a coordination number of 6. Each one of the cells is only going to hold 1 atom. So if you imagine that we have 1 atom at each one of our points on the lattice here, the unit cell is only going to inscribe 1/8 of each one of these atoms. There's going to be 8 of them, and that is, so the overall volume only holds the equivalent of 1 atom. The next structure we want to look at is the body-centered cubic, or BCC solids. They have atoms at each corner and an atom in the center. They lead to a coordination number of 8. And each unit cell is actually able to contain 2 atoms. It's a little bit more efficient way of packing, where we actually have 68% of the cell's volume filled. So if we take a look at what that looks like, it means that we would have an atom at each one of our corners and another one in the center. We can see that here, and our unit cell is going to have those 1/8 of a cell at each corner like we saw in the simple cubic, but it's also going to contain an atom in the center. And so that gives us the 1 atom from each of the 8 eighths, and then the 1 atom in the center. Face-centered cubic solid has a cubic unit cell with atoms at all the corners and at the centers of each of the faces. This is the most efficient means of packing the atoms, and so this is often also called the cubic closest packing structure. It leads to a coordination number of 12, and each unit cell contains 4 atoms. 74% of the overall volume winds up getting filled. So let's see what that looks like. We're going to have 4 atoms that are contained within the lattice structure. We can see that here, where we have 1 atom at each one of the faces poking out, and then we have the ones on the corner. What we wind up with is half an atom being inside of the unit cell on each one of the faces, we have 1, 2, 3, 4, 5, 6 faces, so that's 3 atoms there, plus the 8 eighths at each one of the corner to give us a total count of 4 atoms. So one way that we can look at this, basically what happens is if we look a little wider outside of the unit cell, when we have the face-centered unit cells, there can actually be 2 different kinds of larger structure. So if we move out a little bit, we could have what we call the cubic closest packing that looks like this, where we have each one of these hexagonal layers a little bit off of one another. So this one's going to be skewed a little off from this one, which is going to be skewed a little bit off of this one, and then the pattern repeats. We go back to that first layer that looks like this one, and then it goes off and then back again. Or we could have it so that each one of these layers is alternating as it moves up the crystalline structure. And both of these are going to be slightly different crystalline structures when we look at the whole thing as a whole. There are some other lattice systems. And there's 7 different lattice systems, some of which have more than one type of lattice, for a total of 14 different ones. So we only discussed the cubic ones here, and then touched on the hexagonal. But there are all these other ones as well that can be studied in different ways and have their own different unique properties and stuff. So let's take a look at the structures of ionic crystals. The packing of ions into crystals is more complex than the packing of metal ions because the metal atoms are all the same size. But once we have ions, we're going to have both cations and anions, and they tend to be of different sizes. Stable structures for ionic compounds result when ions of one charge are surrounded by as many ions as possible of the opposite charge, right? So we want to have different charges close together because we know that they attract one another. And when the cations and anions are not in contact with one another because they're going to repel one another because they have the same charge. The structures are determined by 2 principal factors: the relative sizes of the ions and the ratio of the number of positive and negative charges in the compounds, because we know that sometimes we could have, you know, a cation with a +2 charge, and then we're going to have to pack in 2 -1 anions for that guy. So it depends on the ratio between them. Anions tend to be larger, have a larger atomic radius because they've taken on an electron. And so they tend to be packed in the closest packed array sort of configuration. Smaller cations commonly occupy one of 2 types of holes. These are called interstices, or interstitial areas between the anions. There's 2 types of holes that can be found. The hole could be at the center of 4 atoms, in which case it's called a tetrahedral hole, or it can be found at the center of 6 atoms, in which case it's called the octahedral hole. Octahedral holes are larger than tetrahedral holes. Which type of holes form can depend on the size of the cations that you're trying to fit in there. So here we can see the difference between them. So here, for instance, we have 1, 2, 3, 4 atoms, and the area in between them is what we call the tetrahedral hole. Whereas here we have 1, 2, 3, and then 1, 2, 3 atoms on top of it. This leads to a slightly larger little interstitial area right here called the octahedral hole. If the cations are too large to fit into either of those type of holes, the anions may adopt a more open structure. This is what we would call the simple cubic, where we're back to the idea of the simple cubic structure, where we just have an atom at each one of the points, and then that leaves a pretty large area on the inside for those cations to occupy. So now that we've discussed the holes that the cations can occupy, let's talk a little bit about the unit cells that we see in ionic compounds. When we see that we have a 1-to-1 ratio between cations and anions, and they typically, and when they're similar in size, we're going to see a simple cubic sort of structure. So we need a large area for that cation to occupy because it's relatively large in relation to the anions. So we're going to need a simple cubic structure to give it the largest amount of area to occupy. When the ionic compound is composed in a 1-to-1 ratio of cations and anions that differ significantly in size, it's typically crystallized with an FCC unit cell. So in this case here, we can see that we have cations that are able to occupy quite a bit of the unit cell, right? If you start here, which would be like this corner right here, okay, then you're able to fit in 3 cations, 1, 2, 3, and then you would have 3 anions, 1, 2, 3, and then a final cation right here. And we get that propagated out. And these structures can get to be quite complicated too. Zinc sulfide, for instance, has a face-centered cubic structure where the sulfide ions that are very small occupying half of the tetrahedral holes within the structure. So here we have the sulfur is making up a quite large unit cell, and these tiny zinc atoms are just sitting in these little tetrahedral holes inside of the crystal structure. And we're packing quite a bit of atoms into a single unit cell, which means that we have a very complicated structure that we're going to propagate out and repeat throughout the bulk of the material. All right, let's discuss now for a moment X-ray crystallography. X-ray crystallography is a method of determining the crystal structure of a solid by analyzing the diffraction pattern of X-rays. Diffraction is the change in the direction of travel experienced by an electromagnetic wave when it encounters a physical barrier whose dimensions are comparable to those of the wavelength of light. Interference, which is another word that we're going to need to know, is a process by which waves combine to yield either an increase or decrease in amplitude depending upon the phase of the two waves. So let's take a look at that first. So whenever somebody hears this interference thing at first, they think that it's always going to lead to a weaker signal, but that's not actually true. There can be constructive interference and there can be destructive interference. So basically, when two waves come in contact with one another, if the dips and the peaks line up with one another, then they are going to combine to yield lower dips and higher peaks, and the overall amplitude of that wave is going to be higher. But when a dip lines up with the peak of another wave, then they're going to be moving in opposite directions, and they're going to cancel one another out, and you wind up with a lower overall signal. And you can even completely cancel them out if they were the exact same wave and they were what we call 180 degrees out of phase from one another. We can apply this to crystals using something called the Bragg equation. You are going to see some problems using this equation. It's not terribly difficult. It's just another one where we need to pay attention to our units and plug in our values. But when X-rays of a certain wavelength, so that's going to be lambda here, are scattered by atoms in adjacent crystal planes separated by a distance d, they may undergo constructive interference when the difference between the distances traveled by the two waves prior to their combination is an integer factor n of the wavelength. Well, that's kind of complicated, so let's take a look at a picture. So basically, our goal with X-ray diffraction is going to be to determine the distance between two atoms in a crystalline structure. There's a few different ways that this work can be done. Most of the work that I did, what you're going to do is you're going to fix the wavelength of the X-rays that come out, and you're going to adjust this angle. And by adjusting this angle, you can find an angle at which the distance here is going to work out such that when the waves come back out, the peaks and valleys still line up with one another on the other side. Okay? Basically, what's happened is that this wave that had to travel a further distance to get to this guy here before it was diffracted, that increase in distance that it took was just the exact same distance as the wavelength, as the distance from one peak to another on the wave there. And that leads to constructive interference. So by looking for the constructive interference, by getting a clear signal from the machine, because these X-rays are going to come and hit a detector, and knowing what the angle that you hit the surface of the solid with, you can start to determine the distances between the atoms. Similarly, you could have destructive interference. So if you didn't have this angle correct here, then it would diffract off with destructive interference, and you'd get a weaker signal because these guys are not aligned the way that they need to be in order to give you a clear signal up into the machine. There is another way of doing it. This is often typically done doing what they call single crystal X-ray diffraction nowadays. It's a very difficult technique that basically requires you to prepare a single crystal, so as close as possible to a single unit cell into your chamber here. And then you focus the X-rays onto it, and those are going to scatter off into a three-dimensional imaging surface. And then you wind up with these X-ray diffraction patterns. And in the simplest cases, back with like Linus Pauling and stuff, who really started using this technique, they would analyze these by hand. Nowadays, what's going to happen is this is going to go onto a detector. This pattern is going to be fed into a computer, and we use some pretty sophisticated software and statistical techniques to determine the structures that we have.